Hey guys, welcome back to another video. My name is Melina, and today we're going to be going over hydrates and acetals and ketals. So we're going to go over two different mechanisms on how to make hydrates, but one is acid-catalyzed and one is base-catalyzed. We're going to go into how to make a cyanohydrin, introduce you guys to acetals and ketals, and how to use acetals and ketals as protecting groups. So the first reaction we're going to go through is the base-catalyzed hydrate formation. The starting material right here is an aldehyde. You can also use ketones, but just remember that aldehydes are more reactive than ketones, so I'm going to be using aldehyde throughout most of this presentation. And what results is this structure right here, which has two hydroxyl groups attached to one carbon. Remember, this is called a geminal diol. That's another way to say what the product is. But what's basically happening in a hydrate formation is that you have H2O and you're adding water to the carbonyl and you result in this product. So let's go through the mechanism. Oh, before I forget, this is base catalyzed. So of course we're going to be using a base. And since it's base catalyzed, that means throughout the whole mechanism, all the steps are either going to be neutral or have a negative charge. There's never going to be a point where the overall charge is going to be positive. So the first step is happening right here with the base. The base is going to come in and nucleophilic attack the carbonyl carbon, and these electrons are going to get pushed up to this oxygen. And you result in this structure right here where there is the OH attached, and now the oxygen has a negative charge. And with the lone pairs on the negatively charged oxygen, it's just going to grab a hydrogen to do a proton transfer to neutralize itself. So you result in this structure right here. So it's a really simple mechanism, just nucleophilic attack and proton transfer. Next, we're going to go through an acid-catalyzed hydrate formation. So you can see that we're using the same starting material and we end up with the same product. We're just using acid instead of a base. So just like I said with base-catalyzed, with acid-catalyzed, since we're using an acid, all of the steps in this mechanism are either going to be neutral or positive. There's never going to be a point where there's going to have a negative charge. So the first thing that happens in this reaction is not nucleophilic attack. What actually happens is you're going to do a proton transfer to activate this carbonyl. So you attach the acidic hydrogen to this oxygen, and now that the carbonyl is more activated, you can add the water. So the lone pairs on this oxygen from the water are going to nucleophilic attack the carbonyl carbon, and these electrons get pushed up. And now you have a neutral hydroxyl group right here. But then now you have this positive charge because you added the water. Now what you want to do is with another molecule of water, that's just going to proton transfer and take off one of the extra hydrogens that's on this molecule. And then you end up with a neutral product, your hydrate, geminal diol. So yeah, this acid-catalyzed hydrate formation is just an extra step compared to the base-catalyzed. You just have to remember to activate the starting material first. This is just because if you were to do a nucleophilic attack first, you would result in something that has a strongly basic portion and a strongly acidic portion, and it just doesn't work out. So that's why we have to activate it first with the acid. Next, we're just going to go into cyanohydrin formation. This is basically, it looks extremely similar, except instead of another hydroxyl group, we have a CN attached. So what happens, it's basically the same thing as the base-catalyzed formation reaction. So the CN minus is going to come in and nucleophilic attack the carbonyl carbon. These electrons get pushed up. You have a negative charge on this oxygen, so it's going to pick up a hydrogen, an acidic hydrogen. This is coming from the HCl, and you result in a neutral product. Next, we're going to go into acetals and ketals. A lot of people I've been noticing are struggling with the difference between acetals and ketals. Just know that it's basically the same thing, like the same mechanism, except the only thing that's different is what you're starting with. That's what differentiates if the product is going to be an acetal or a ketal. So see, I provided a aldehyde and a ketone. The reagents are the same, and then this aldehyde results in an acetal, and this ketone results in a ketal. So see, the only difference is that instead of a hydrogen, the ketone has an additional carbon. And then if you look at the products, they're basically the same, except the ketal has an additional carbon attached. So let's go through the mechanism. This is a really long mechanism, and so I took this from Dr. Castleman's slides from the lecture, and so let's go through it. So this is an aldehyde. Remember, we've been saying that aldehydes are more reactive than ketones, so that's why we've been sticking to aldehydes, but just know that you can do the reaction with a ketone, and that's what would result in a ketal. But since we're starting off with an acetal, this would result, oh, so we're starting off with an aldehyde, that's why the product is an acetal. But it's the same mechanism. So the aldehyde is going to act as the electrophile, and you're going to react it with a weak nucleophile. So the first thing that happens is we have to activate the aldehyde with an acidic hydrogen that comes from the catalyzed H+. Remember, this is very similar to this mechanism, the acid-catalyzed hydrate formation. You have to activate the aldehyde first. So going back, we activate the aldehyde, and now your weak nucleophile right here is going to nucleophilic attack the carbonyl carbon, and these electrons get pushed up. You result in a OH right here, now neutral, and it's attached, this other oxygen is attached. This oxygen right here comes from this structure right here, the nucleophile. Now what's going to happen is, see this hydrogen, you don't want it right there. You want to move it to this oxygen right here so it forms water and it can leave. So what we're going to do is we're going to take another equivalent of the nucleophile, and it's going to grab that hydrogen off right here. And then in the next step, we're going to have this oxygen grab that same hydrogen off, if that makes sense. Can everyone see that? So if I were to, let's see, I can draw. Okay, so this hydrogen, I'll use red. This hydrogen right here is the same one that's right here. And then when this oxygen takes this hydrogen off, it forms this H2O. Good, okay. So let's go back to this. So now that you have water, the water can leave, and you form this structure right here. And there's a positive charge, but it's kind of weird for the positive charge to be there, and we want a more stabilized structure. So we use the lone pairs on the oxygen to form a resonance structure, and you form this structure right here, which is more stabilized. And this yellow portion right here, if you look, it is an aldehyde. Like this structure that's highlighted, it looks like an aldehyde, right? There is an oxygen, a double bond to carbon, one R group, and a hydrogen coming off right here. So what happens next is basically the reaction occurs again. Like this step right here. We have the nucleophile coming in to attack the quote unquote like carbonyl carbon, and these electrons get pushed up, and you form this structure right here. And then you have another equivalent of the nucleophile coming in to take off that extra hydrogen, and you form your neutral product. So the acetal is the, it has two of the OR linkages to the same carbon, two ether linkages to the same carbon. Good, okay. And then remember, if we were to do this with a ketone, there would just be an extra carbon coming off right here, and that would result in a ketal. So next, we can go to how to use these as protecting groups. Oh, let's erase these. Erase. Okay. So acetals and ketals as protecting groups. So like I've been saying, aldehydes are more reactive than ketones. So if we were to react this structure that has an aldehyde and a ketone with these reagents right here, that one equivalent, I spelled equivalent wrong. This should say equivalent. But if we were to react this structure with one equivalent of these reagents right here, only the aldehyde would react because we have one equivalent and the aldehyde is more reactive. So this leaves the this leaves the aldehyde capped. So remember, the purpose of protecting groups is to put a cap on a specific portion of the structure so that it is no longer reactive and you can go through with another reaction. So we put a protecting group on the aldehyde, and so the aldehyde is now capped, leaving the ketones still able to react in another reaction. And then say you go through another reaction, and then now you need to take the protecting group off, right? You need to take the cap off. So how to take the protecting group off, you use catalyzed H plus and H2O, and it brings it back to the aldehyde. So let's go through with another example of how this is applied. Okay. So here we have a structure that has an aldehyde portion and a ketone portion. And we have one equivalent of the protecting group reagents. So this goes through, and remember I said the aldehyde is going to react because the aldehyde is more reactive than the ketone, and we only have one equivalent. So that one equivalent is going to react with the aldehyde. So the aldehyde is now capped. And now we can go through with a Grignard reaction, right? So we go through with the Grignard reaction, and the Grignard is going to react with the ketone, which results in this right here. So this is, yeah, so it results right here. And then now that we have the ketone reacted with the Grignard, we have to take off the protecting group. We have to take off the cap, right? So we use the reagents, catalyzed H plus and H2O, and it brings it back to the aldehyde, and you get your final product. So yeah, so that's all I have for today, guys. Thank you guys so much for watching, and I hope this helped.